welcome to Beyond the Qubit. Today we have Johannes Jobst. Johannes is CEO of QuantaMap. And QuantaMap is really solving an exciting bottleneck in the industry. It does chip inspection for quantum computers. And QuantaMap can see errors that normal inspection tools cannot see that. So with that, welcome Johannes. I'm glad you are here. Can you explain in basic terms how your technology works? And maybe let's start with how do you measure quantum models? Quantum modes.
Okay, then maybe I have to take one somewhat bigger step back. So what we at the heart of our technology is what's called a SQUID, a superconducting quantum interference device. And what this in essence is a ring of a superconductor, so a material that has zero resistance at low temperatures. And then you make basically a cut through the ring and have two what's called weak links. So basically two small cuts, let's call them cuts, where it's not superconducting. And then the superconducting electrons, they have to tunnel from left to right. So quantum tunneling. And the details maybe don't matter so much, but what's the important thing is that this makes it extremely sensitive to very, very subtle changes. And one of the changes that can happen is that because it's a ring, if there's a magnetic field that goes through this ring, it changes what's called the phase of this electron. So basically it's a bit difficult to explain, but basically it changes how this electron tunnels, and therefore it changes the signal on the sensor by a huge amount, even for very, very subtle fields. And then we really make use of the fact that it's a quantum mechanical effect. And in a sense, what's the pain for the chips? That they are very sensitive to everything. We use to our advantage to build a very, very sensitive sensor. And then those SQUIDs, quite ancient technology, probably exists, 50 years or so. But what our core technology is to make them really small and put them on the tip of a very sharp needle. And we need to do this because then we use this needle to scan over the chip. And what that basically does is that the needle, one step back. So that we measure the force, atomic.
I love the technical details, so yes. Thank you for explaining that.
What we basically do is we measure the atomic force between this needle and the chip to make sure that it's always only a few nanometers away. And then if there's a step in the chip, for example, because there's some structure, electrical line, whatever, the needle is automatically retracted by the right amount to follow this topography. And that's also an established method. It's called atomic force microscopy. And what it basically does is it gives you a 3D topographic map of your chip, which is nice, right? Then you see the structure of the chip. But as we discussed earlier, the structure is typically not telling you anything because in structure, everything looks just perfect. But what it does for us is that it makes sure that this sensor stays always at a constant and very close height over the chip, which means we bring the sensor very close to what we want to measure. And then we have a extremely sensitive sensor extremely close to the chip and at a safe distance, because we have this feedback. We don't crash into the chip and damage the chip. And that is basically the core technology. And this whole thing needs to go down to very low temperatures, which makes everything a bit harder to integrate, but it's necessary because we need to operate the chip at its working point, and the sensor we have also needs to work at low temperatures. That's sort of the technology at its core.
Thank you. And why is it important to measure multiple and different observations? And then you mentioned already magnetic fields and electrical currents, local temperature and hotspots, and the chip surface.
Yeah. Just let's be a bit cheeky, right? The more the better. But which is sort of always true, right? The more insights you have, the more things you can combine. But if we're a bit more serious about it, the quantum chips are built on what's called quantum materials. So they're just complicated materials. Superconductors are just complicated. And to understand properly how they work, and in the end, what we're really trying to to quantify is where things go wrong, so how it works. It's typically not only one parameter that tells the full story, but you want to look at the problem from different angles and combine the insights all in one go. And that's sort of one nice thing about our method, because the sensor is directly on the needle. We take all the data in at the same time. So we don't need to worry about aligning different images that were taken in different scans. And then you get this multimodal imaging, and you can, for example, compare. Okay, I can now not show the figure, but it's very instructive actually, where you see a structure where the current, basically a electrical path that you just see the structure in. Then we see that there are static magnetic defects that shouldn't be there, but we spotted them. And then you see how the current is avoiding those magnetic defects. And then you basically already combine three things in one. Yeah, basically then if you could make the same argument for a current path and local temperature, and typically, if you combine all those insights, then that allows you to make a better assessment of the situation, and therefore a better assessment of what you need to change to improve the problem that you're seeing.
And how do you do that? Do you have some kind of reinforcement learning? Or ASML, for example, they have measurements, and then they adjust the tool based on the real-time measurement. Is that in your product roadmap? Is that how does that work? It's a bit new.
Indeed, no, it's for sure in the roadmap, but in the relatively far future, because this really only makes sense once you have a tool that is somehow integrated into a high volume fab, and then indeed you can do this feedback. But at the moment, we and also the whole quantum industry is still quite a few steps earlier. Yeah, basically we need to identify what are the defects that matter, where do they come from, which process do we in the end actually need to supervise to do this process control on. And there at the moment, the way this works is that we really work intimately with the customers, because they of course have the deep insights on how the chip was designed, how it's supposed to function, what the materials are, and so forth. That's information that they sometimes can share, sometimes they cannot share, and there we need to go a bit back and forth to really come to a common understanding of what to do next and how to identify what needs improvement.
We talked already a little bit about it, but I want to come back on it because it's one key element of your technology. Can you describe in basic terms what is a nanosquid quantum sensor and how does this work? Is this the ring?
Yes, correct.
That's the ring.
Correct, right? So the squid is this ring, and it's a nanosquid because we can make it really small, a few hundred nanometers across, because then that basically determines the resolution you have with a quantum imaging. The bigger you make the squid, the more sensitive it is. But then also if you make it 1 micron, then everything will be blurred up to 1 micron, and that's maybe already a bit too big to see some of the features. For other things, a micron is perfectly good enough, but typically we try to make it smaller to sort of optimize sensitivity versus resolution.
You talk about imaging, local temperature rise, electrical currents, and magnetic fields. Why do those signals matter for quantum devices?
That's a very good question. So they all are slightly different, right? So for the magnetic imaging, we need to image the currents, because the currents, they generate a magnetic field, and that we want to image. So that's very easy. Then there's static magnetic defects, and most notable, there's something.
What is that?
Yes, exactly. The most notable, there's something that's called a vortex, which is, in essence, it's a small current that goes around in a circle. Really a small circle, few tens of nanometers typically, that forms because the superconductor really does not want magnetic field going through it. It expels the magnetic field, but then there's always a bit of magnetic field left. Right? There's Earth magnetic field. People take good care to shield as much of it as they can, but it's never perfect. Also with driving with the currents, you generate magnetic fields, and those vortices, it's just a thing that superconductors do, and they are potentially problematic, especially if they are close to your qubits and if they move. And because they're magnetic objects, if you pass a current, they will interact with this current. So then if they're around, they most likely distort the driving or readout signals of the qubit, and that's really a problem because then you're sort of doing the wrong computation. So imaging where these vortices are is super important for the chip designers because they go at great length to try to suppress them, and we can very easily sort of quantify and prove how well those measures work. And that again sort of feeds back into the design. So therefore, we do magnetic imaging. Then the electrical image, or the temperature, really is pinpointing at subtle, very very subtle electrical defects. Because normally the superconductor has no resistance, so there's no power dissipated. If there is an area that's less perfect, you can drive it such that it slowly starts to warm up. And then you can really like pinpoint where this is. And then if I say warm up, I really mean it warms up by a millikelvin or a few hundred microkelvin or so.
Yeah, but because it cannot not warm up too much because you have very limited energy budget in the cryostat. And is it that's another thing? Is the nanosquid, is that inside the cryostat, or where exactly does it sit?
Yes, so the whole microscope we're building is inside the cryostat, so we completely cool it down to typically below 1 Kelvin. And the squid is really just directly above the quantum chip. So therefore, ideally, it has the same temperature as the quantum chip.
And what is the maximum energy that you could generate with the nanosquid before disturbances in the quantum mechanics or decoherence starts to happen?
Yes, I don't know how much we would need to push through it, but I think quite a bit, because or quite a lot more than we need to do to read it out. That's exactly how we designed the technology. We wanted to go for something that's really passively electrically read out, that we're as non-invasive as possible.
Okay, because when I spoke to Delft Circuits, they also mentioned that it's really important that you keep the energy and the heat very low.
Exactly. Now, and the advantage is that the squid, because it's very small, we get away with really, really small currents that we need to pass, and it only has a few wires that we need to connect, right? So compared to what Delft Circuits is doing, and what a lot of the quantum architectures are struggling with, is that you just need a lot of cables, like thousands of cables, and that all those cables also generate extra heat loads. There we're good.
Yeah.
With 10 cables, we can do everything we need to do. So that's in a sense easy.
Are you also using the cables of Delft Circuit?
Actually, yes. So we're in or not quite yet. We're in a project with Delft Circuits and Infineon and a few other partners. And one of the things that we indeed want to do is to see if their cables are suitable for our application, because they're of course optimized really more for quantum compute, and we have slightly different requirements, and we want to see if there's a good match. And I think there is, but we're not even halfway through the project, so there's still many things to find out.
What is the role of quantum sensors in your systems?
And they're really at the heart of it, right? So this squid is a quantum sensor, and it's the key distinguishing factor that we're having. AFM is a relatively established method, and therefore really this adding the quantum sensor and interpreting the information that comes out of it, this is really our core added benefit and core technology.
What is cryogenic scanning? Why is it important for the use case?
So a lot of the chips, they work at low temperatures, and very often 10 millikelvin or 20 millikelvin or so, to suppress all these two-level systems that we talked about before, and like general thermal fluctuations. But even before that, they just behave very different at low temperatures than at room temperature, which also means that if you want to test the defects that determine the performance, you will not find them at room temperature. At room temperature, if something looks wrong, it's for sure a problem, but even if it looks good at room temperature, it doesn't tell you really anything, and therefore all the inspection needs to happen at cryogenic temperatures. And then not all of it needs to happen at 10 or 20 millikelvin. 1 Kelvin is typically enough. As long as everything is superconducting, now we can already do a lot. But that's sort of the bare minimum, that all the superconductors on the chip, they should be superconducting. And that just requires low temperatures. And that is also one of the more complex parts of the tools that we're building, is that basically the whole tool needs to operate at those low temperatures.
What level of spatial resolution or sensitivity is needed before this decision becomes useful for customers?
It's a bit of a sliding scale. So right at the moment, what we're having is we have, let's say, 200 nanometer spatial resolution with a sensor. With the AFM, it's much better. It's below 10 nanometers, and sensitivity we already touched upon. It's better than a millikelvin for thermal, better than a micro Tesla magnetic, and those specifications are already plenty good enough to add value to customers, right? So we did commercial pilots with a few chip producers. They were all super happy. They all learned something about their chips that they had no idea was on the chip. And in general, our signal quality is already really good. Moving forward, I think, depending a bit on the use case, there are two things that we still want to optimize. It's spatial resolution, but that always comes at a trade-off with sensitivity. But some use cases, you just want to be more on the resolution side than on the sensitivity side. And the other thing that we really still want to improve on is throughput, because at the moment it's very workable and the system is super stable, so you can just let it run for 12 hours straight if it needs to, or 24 hours. You just run it over the weekend with a complex recipe of measurements. But on the long run, of course, throughput will become an important KPI, and that's something that we really still want to improve, and there's also still quite a lot of room for improvement on that front.
Can you give examples of defects of losses that you found with your measurements that were not able to be found without?
Yeah. Maybe there are three things that I think I can mention. So one was a very, very clear case from a spin qubit from TNO here in the Netherlands. And this is an extremely complicated chip, right? The spin qubits, they have all like buried gates and very small structures and many lithography steps and deposition steps and whatnot to define the spin qubits. And then what that particular architecture does, it has magnets on top that define the energy levels of the individual qubits. And what they would always see is that they go through the whole fabrication, and then the energy of the qubits would be something else than they were thinking. And then, of course, you're exactly in the problem that I sketched before. You have no idea which of the many process steps to blame. And what we could do is to measure the full chip at operating conditions and really identify.
Okay, can you walk us through who is your competition?
I think our strongest competition at the moment is the business as usual. Right, that people have their routines. They make the chips, they do this wafer dicing, and then sort of trying to figure it all out at the end, or maybe building somewhat simplified test chips and measuring those. And there we still need to educate our customers a bit that there's a new technology on the market that can really help them. That's in addition to what they're currently doing, right? It's not completely replacing, or is really an addition, but an addition that speeds up. So that's I think that in a sense the biggest competition. And then there are a few other companies that try to maybe do something similar. Most notable are there's also scanning techniques that are based on NV-centered diamonds. So they're basically two, one's QNAMI and QSaber, and they are traditionally working at room temperature, which is, of course, a big benefit if you want to study stuff that happens at room temperature, because we can't. But they are now also starting to develop tools for cryogenics, and that could potentially be a competitor. I am not so worried, because to read out those NV centers, you need to shine a laser and a RF, so a radio frequency microwave signal, onto the diamond. And the diamond is very close to the quantum chip, which basically automatically means you're shining your beam also on the chip. And therefore, I think they will just disturb the chip a lot by those signals and mainly measure the interaction with their driving signal and not the intrinsic properties of the chip. And if I'm not so worried that that they are real competitors, but yeah, we keep our eyes open.
Yeah. Other competitors?
Not that I'm aware of.
So maybe to summarize, your biggest competitors, people are producing chips without your measurement tools, and what you do in a cryogenic state, that measurement, that's not done at the moment. There are things who do it, a few competitors who do it at room temperature, and one of them is moving to a cryogenic environment. However, it's done with NV diamonds and with a laser, and that might cause disturbances, and therefore you're not so worried at the moment.
Correct.
Can you walk us through the barriers to entry for competition? So for me, it sounds like you have a really cool product, a really interesting niche that you can focus on. And at the moment, there's very little competition, but it's a very important enabler. So if somebody wants to copy you, what are the barriers to entry for them to copy you? What are the main risks, and how can you raise the barriers to entry?
Yeah. It's sort of multifaceted. There, I think two important ones is that we have patented the core technology of those squid on the AFM tip, which already puts up quite a bit of a barrier. There are ways around it. There are things published in literature that you can just use the prior art to get at least in the vicinity of what we're doing. But then there's really a lot of practical know-how that is not really patented and also not in the public domain of how to actually do it, which will there I think we're really a few years ahead of any potential competition. And then the third, and that will become increasingly important, is really the application knowledge. To my knowledge, we're really the only company so far that has studied quantum chips with any similar method, and we're now working with the producers to interpret the results, to fine-tune the methods, and we have just started, right? So the longer our head start lasts, the bigger this barrier will become. There might be things also to still cast into a patent, but even if not, this application knowledge is extremely difficult to replicate, because you basically need to work together with the producers to build it.
And in semiconductors, typically it's also the case that the manufacturers are very reluctant to change suppliers. So once
Correct.
they're working with you, they're
Correct.
not willing to take technology risk.
Correct. And that's also, again, why we think that the timing is good, right? We can now sort of grow up with the R&D teams of the producers, and then they know exactly the technology. So then if we can provide a tool that does volume inspection based on the same technology, they already know how to use it. They know what they can learn from it. And then we think it will be very, very hard for a competitor to break in at that stage.
Okay, that's clear. Thank you, Johannes. What do you want to achieve for the coming 5 years?
Basically, to become the de facto standard for chip diagnostics, and that there will be no fab that produces high quality quantum chips that runs without one of our tools.
That would be amazing.
But in a sense, it's really ASML playbook. It's a relatively small niche, but if your technology is strong enough and people cannot do it without, you are in a very, very strong position. And since we think the quantum market will really expand very rapidly, this is really also the corner that we want to protect as hard as we can. And therefore, so that's really the goal. And the way to get there is to really, as said, to now already work with customers, get a tool there ASAP, and then with every improvement step that we do, bring them to the R&D departments to really be ready to scale when they are.
What are the building blocks that are still missing?
So for the R&D tool, a lot of it is already there. All the this fundamental risks we mitigated. It works beautifully by now. It was quite a lot of hard work to get there, but okay, that's a different story. And now there is really still engineering risk, sort of system risk, right? It's a complex system, and all the components need to work together sort of flawlessly. And there we still want to improve robustness a bit, and we want to improve user friendliness. Right, at the moment, you really need a very, very well-trained user to operate it, and that's something that's also relatively clear how to do. And then the third one, which is at the moment still a bit less clear, is that we really try to standardize a bit the measurement protocols. And then again, it depends a bit on exactly the custom architecture, and we might need to tailor it a bit to the customer, but at least that it's clear if this is what you want to know, this is the recipe you run, and then all the pipeline of data acquisition and data interpretation is just standardized. And that's sort of for the R&D tool. And then moving forward, I think that the hardest problem to solve for a volume tool will be throughput. And that's both loading samples, because you don't, at the moment we warm up and cool down the whole microscope. And this is relatively fast. 24 hours we can be cold to cold. So warm up and cool down in 24 hours, which for quantum is actually really fast. But of course, in any real terms, fab terms, is really slow. So it's wafer handling speed, and then also really data acquisition speed. There we also still want to become better.
Okay. How do you compare, and where do you differ with Orange Quantum Systems? You both do quantum chip testing. Orange Quantum System is really quantum chip testing, and you within quantum chip testing you specify certain you try to find some certain errors. What is different, and how do you enable each other? Where are you complementary, and what is different?
Yeah, exactly. Complementary is exactly the right word, because they really test at the end of manufacturing, right, the full chips, and they can measure quantitative performance parameters. They can measure the coherence time, they can measure crosstalk, and all the things that they really care about, that you can sort of feed back into the computation. What they cannot tell you, if one of those parameters is not good, why it's not good. And for us, it's exactly the opposite. We can identify structures that are defective, but we cannot predict the quantitative impact this will have on coherence time, for example.
That's really cool that you reinforce each other.
Yes, and we just wrapped up a collaboration project, a subsidized collaboration project. Or now we will officially wrap it up end of the month, and then we just got awarded a follow-up project to really build further on this pipeline, to really make sure that it's also integrated process, because in the end we both believe that if you want to make good quantum chips, you want both tools, and you want both tools to also talk to each other, and then in the end also talk to your production tools, right? It's what we discussed before. You just really want a good data platform of all the things you learn about your chips and how you produce them, and this all needs to work together.
Can we talk a little bit about the value for the customers? What product and services do you offer to your customers?
So at the moment what we offer is that we basically do measurements as a service, diagnostics as a service. Customers can send us a chip, we agree on a test plan, and then we perform the measurements and do the data analysis. And that is at the moment a very nice model for our customers to sort of get easy access to the technology, try it out without huge investments. But then on the long run, we of course really want to sell tools, and we also think that our customers want to buy tools because they really want to own the whole process, right? You don't want to ship chips always across the ocean and be sort of dependent on someone else. I know you want to be able to, or you want to enable your own team to go from design to simulation to verification and sort of really close the loop. And so basically system sales is the other thing that we're offering. And then, as we discussed, right, those probes, quantum probes, they wear out over time. They're quite stable, but every now and then they die, especially if you make a user error. And This is also one of our products that we really sell those probes. It's a nice recurring revenue stream.
Okay. And how do you monetize the services?
We have a business model how to price it, and I think at the moment we're doing, in a sense, we're doing very fair prices for the customers, because we also still are learning along the way, and so far everyone has gotten a really good bargain.
Okay. I don't know if it's customer centric, then don't talk about it, but can you maybe in general terms walk us through the business momentum?
Now, we already touched upon some of the things. We just finished a commercial pilot with Rigetti Computing, and we are working very intensely with Quantware, and we are talking to a double-digit number of companies that are interested. So I think momentum is good. And now we need to convert some of those discussions.
Okay, now that's interesting timing. And okay. And what are the biggest challenges in selling instrumentation to an emerging industry?
It's really educating the customer. We need to make clear that this additional tool will really add value to their team and really speed things up. And it's not just the extra thing you do that basically eats time and money, and that we really still need to quantify how much this benefit is, and that we try to basically do via this diagnostic as a service, because then people also really get an idea of, okay, how long does it take to do those measurements, what exactly is the outcome, what can we do with the results, and then I think they have to learn, we have to learn together to really fine-tune.
What typical budget does this come? So that you still need to educate the customer, but if they say yes, what are the potential budgets that they can use to fund this? Do they have the money ready, available, or do they need to raise additional money for this, or how does that work?
Depends a lot on the company. For some of the smaller ones, it might really be a relatively big investment, but then for a company like Rigetti Computing, they're sitting on a few $100 million cash. So for them, this, if they want, it's really not a problem. And also for most of the other quantum chip companies, they all raised money relatively recently, specifically to build up production capabilities. There's really this push from lab to fab, how they call it. So in a sense, timing is very good. The people are really now starting to look into which tools, and there is in principle budget available. Budget is of course always tight, right? Like let's not fool ourselves. We're selling an expensive piece of equipment, and the discussions always take time, and they're also not everyone will immediately buy, right? We have to be realistic there.
Johannes, can you walk us through the management team? Who are the key people and what do they contribute?
So basically, let's start with myself, right? We talked already a bit, but I do all the non-technical work, even though I have a technical background, but I really have to start to let go more and more of meddling with the technical discussions. And then my two co-founders are really domain experts in the two things we're doing. So Kave he's also a professor here in Leiden. But he's one of the leading experts for those quantum sensors, and he invented the process step to really put them on the AFM tips, right? So I think there's no one else who can do this better. And Milan, he is, also think one of the leading experts in building low temperature scanning probe microscopy setups. He's been doing this for his whole career, and so they really both have an extremely strong technical component on our core technology. And then maybe two other people that is somewhat extended leadership team, which is Dan. He's our system architect, who's really responsible for most of the system development, and he has a background in microscopy. He worked at a different startup before, and I also know him already for 10 years, so I'm very happy that he joined. He was one of the first people to join. And then we have Jeslyn, who is leading our diagnostics as a service business, and she yeah, she's really a magician when it comes to measuring and interpreting data and data analysis, coding. So
Okay.
that's sort of the split.
Thank you for explaining. Let's talk a little bit about your personal drive. Where do you get energy from?
So for me, what I really enjoy is working sort of on the boundary between technology and people. So what I mean by this is I would find it very hard to work in a company that does something that's not really, really difficult technology. But at the same time, even though I enjoyed this a lot during my PhD, I get more energy from not being only in the lab, but really talking with people, enabling people, and looking somewhat at the bigger picture. But for me, it's really this combination. Also, the fact that I do many things, and that I really switch between very different tasks. Right? It's sometimes I'm joining a very deep technical discussion, and it's very high level strategy. Then I'm recording a podcast, right? The outgoing things, sales discussions. It's super broad, and that really energizes me a lot, because you need to switch all the time, and then wake up, you go, and I enjoy it a lot.
How do you decide what to focus on?
Very often, there are a lot of things that need to happen, and very often only the urgent and important things happen, and that's always the first thing to tackle. And the challenge sometimes is to also make room for the important but not urgent things, and that I try to plan such that I still spend sufficient time on those things, and I basically try to prioritize based on those two metrics.
Where do you decide not to focus on?
I try to outsource as much as possible of admin tasks, because we're still a relatively small startup, and basically all the non-technical things are on my plate at first, and I really try to find either external suppliers or someone within the team to hand over some of those things, and that is an active effort at the moment to be able to focus a bit more on big picture and say.
Okay, that's clear. What are the must-win battles for QuantaMap for the coming 5 years?
So the most urgent one, in a sense, is quantifying value add and getting one system into, or better, two systems at customer locations, to really build this fear of missing out for other companies. And I think that's the key battle to win. And once we have won that, then the next one is to really prove that we can deliver yield improvement as a process monitoring tool. Those are sort of the two things, because they're slightly different markets, and those two things we really need to prove.
How do you scale up the company from a startup towards potentially a mid-cap in 5-10 years down the road?
Yeah. There are, again, sort of two things that need to happen that are also slightly different in their requirements. For the selling of tools, the scale-up, in a sense, is relatively simple, and that's also because, in the Netherlands, there's this really fantastic ecosystem of suppliers that we can rely on. So we don't have production machines. All the custom parts, they come from the same suppliers that ASML and those kind of companies also use, and there's just a fantastic ecosystem out there. So that scale up is really, in a sense, simple. You just tell them, I don't need 2 of those, I need 20, and then they make it. And then the challenge in the scale up will be to assemble and test and establish protocols to do this consistently. And there, I think the way that I learned it from semiconductor tooling is just perfectly suited. And lucky enough, we're now here in the incubator space where the whole ground floor is still empty, so we have plenty of room to also grow. Once we have filled the 200 square meters we have here, we will need to look for a separate building, but I think we can do a lot in the building we're currently in. The other thing that we're not entirely sure yet how to scale is the probe manufacturing. So with every tool in the field and with the usage of the tool, we need more probes because they're consumables, and there we will need to decide a bit how the split will be between outsourcing production steps and doing things in-house, because the tools are quite expensive, right? Those nanofabrication tools and clean room is just quite an investment. And yeah, there we will see a bit how things evolve, how fast and in which order we will buy tools.
Okay. And how do you manage your cost base? How do you think about fixed cost versus variable cost?
Mm-hmm. At the moment, our biggest cost are people, and that will remain true, I think, for the foreseeable future. Apart from, and that's also a not negligible cost of goods, but that of course is always linked to some sale. Basically, those costs only come once there's a PO, and therefore the costs are relatively simple to manage at this point. Once we start building a clean room, things will be very different. But that's exactly why this is a strategic decision that we will probably make somewhere 1 or 2 years down the line.
Could you describe the culture of QuantaMap?
I think we have a very nice atmosphere in the team. Everyone really is really working hard on the things that they need to focus on. Everyone is also happy to switch focus relatively quickly, as it's sometimes needed. And yeah, everyone can really work together with everyone quite well. And yeah.
But maybe what are so for me, if I talk about culture, it is also about lessons learned, and it is about the culture is set when mistakes happen, and then how do you react? So either it's underperformance, or you have to make a decision. We have to let go somebody, or something is not working, and then it's about, okay, how does the top? What is the message from the top, from the CEO and the CFO? And of course, you're still small, but it's important, especially for the coming years, if you scale. What is the message that you want to give? And then what are the key things that happened with QuantaMap that you say that really determined who we are?
Mm-hmm. So far, lucky enough, there was no really big mistake we made, I think. Small mistakes happen all the time.
And they are part of a startup, right? That's exactly right. Failing fast. So
exactly. In a sense, if you don't make mistakes, you're not trying hard enough. And I think this is maybe sort of the culture that we also try to have, right? That we're not full on cowboys. We try to think through decisions and go step by step. But also at some point, it's just clear that you need to decide and just accept that maybe it's the wrong decision, or that you make a mistake somewhere along the way, and that then it's typically not one person to be blamed for this mistake, right? We own the decisions, and we own the mistakes we make as a team. And that, I think, produces a really safe environment for people to also just try things, because it's important that everyone, as I said, right, everyone should have as much ownership and responsibility as possible, and also feel the confidence that they can try things.
Okay. One of the things what I hear quite a lot from startups in quantum technology is that some still have quite an academic culture. Mm-hmm. And there's quite a difference between being an enterprise and having an academic background. For example, Stefan Hengerspager, he had an interesting observation when he became CEO of Quix Quantum. He said the people from the academic background, they were used of publishing papers. But publishing papers is not always in the interest of your company, with patents and trade secrets. Do you have examples? How is that an issue in the culture of QuantaMap, the academic background? And what
I fully subscribe to this, right? That's also what I mean with the whole quantum industry is still very, very much in the R&D phase. It's very researchy. And for us, the same is true. For us, papers are still an extremely good way of publicity, and therefore we actively are writing papers. We just had a paper published 3 weeks ago or so. And therefore, part of this academic mindset we also really want to keep. At the same time, indeed, we're not a university, right? So at the end of the day, we need to earn money. We need to make customers happy, and for that, or diagnostics as a business is a really very good mode of sort of bringing this into the team, because then we immediately work with customers. We really need to have a sort of a professional way of handling this. That so far has really worked quite well, because a lot of our team indeed has an academic background.
Okay, can we talk maybe a little bit on your conviction that you are a big success, and what needs to happen that you say, if this happens, then my conviction goes up? And then let's assume the conviction that you become the next ASMI or the next BASI or the next ASML.
Yes. Now, I think my conviction will really increase dramatically if, or when, I should better say, when one of our tools really is in a real leading quantum company production line actively used, right? It's not just there and they use it every now and then, but no, it's really something that they rely on. And that to me will really be the proof point.
And why is that? Why does your conviction, if that happens, then your conviction goes up?
Because then I think we have really proven what we all believe to be true, namely that people need our tool, and right, that's one thing, and then we have also proven that they realize it. I think is really critical, because we can of course believe this ourselves, but if our customers don't believe it, it's only half useful.
How much capital do you need to scale? And what do you target to achieve with this money?
Yes, so first good news, right? So we just were awarded the EIC Accelerator, which is 2.5 million grant, and then they double investment round of up to 15 million, which is really good, right? This is sort of the right amount of money that we need to go to this volume tool that I described, and then from there we will need more for the scale-up phase. But what we're currently looking at is to really sort of fast track some of the fundraising, so not really a full round. We're trying to do sort of a pre-round with one or maybe two investors for 2 million or so to really now boost and bring the prototype tool that we have to an industrialized R&D tool. And that's what we said earlier. This I really want to have done next year, and for that we need to put a bit more on the gas pedal.
Okay, now that sounds interesting. And what can you... So with the 2 million, that brings you to the production tool?
Yes, to the R&D tool. Right? But
the R&D tool.
But we really need to go from what we now have in the lab to an actual product. And for that we will need, I think, roughly 4 million. So the EIC grant plus 2 million.
And the R&D tool, is that the tool that you talked about? If that's at the customer, that then your conviction up, or is it a tool in between?
It's already a tool in between, right? So we will now ship one to Quantware. That's already confirmed, and I target to sell another one. And basically, those the earliest tools I get into a customer, that will really drive conviction, because that proves the two things I said before, plus that they are also able to operate it by themselves. And those are really just important ingredients to make this all work.
Johannes, can you walk us through the positive flywheel? Why can you innovate the fastest?
Because we really built a product with this whole quantum first idea, right? We first settled on, okay, we want to do quantum. That's how we built the product, and we from the start engaged with customers. Quantware was there really from day one, and now with this early access via Diagnostics as a service, this is how we really can iterate super quickly together with the customers. And I think this is required, that we don't develop a product sort of in the vacuum of our own imagination, but that we challenge what we build, that we challenge what it does on a customer chip with a customer feedback who has paid for it, because only then it shows that they really want it. And we're currently doing this, and this I think will really start a very productive process of back and forth and really spin up the flywheel.
Okay, that sounds cool. What would you do if you had unlimited amount of money? What could you do with that? What problems could you solve that you cannot solve today? Think about doing things in parallel, or or what can you front load? Are there certain companies you say, well, that might be interesting to acquire, or if I put a few things together, then I can solve really important bottlenecks? What would that be? And not specific in company names, because I would keep that for yourself, but more in general terms. Are there other things that you say, well, I have plenty enough of opportunities to allocate capital?
Yeah. I think with unlimited money, we could basically move faster towards a fast or high throughput tool, because that really requires quite a high investment in development, of course, but also parts and clean room and everything, which at the moment we really want to first see traction from the R&D tool before we do this. But that, of course, intrinsically leads to a delay. And if I had unlimited capital, I would already put much more effort into this, scale up the team, outsource a bunch of things, and really just accelerate that way. And I think we could probably win a year or two.
Maybe to wrap it up, Johannes. So first of all, thank you. It was an amazing call. I learned a lot. Can you maybe wrap it up with a 2-minute summary? For investors, why is QuantaMap interesting to track in the value chain as an investing?
Yes, so QuantaMap really does something that no one else does, and something that we strongly believe will be a key ingredient to a successful quantum industry as a whole. And that is to make sure that the companies that produce quantum chips can do so in a scalable way. Right, and that is really enabling all of quantum. If this becomes a niche where it's hard to make a single chip, the whole promise will not happen. And in that sense, we're really having a very important position in a fast-growing market, and therefore I think we're an excellent investment if you're into deep tech.